Imagine watching a glass fall from a table, shatter, and then the shards leap back together, rise, and land perfectly whole. Absurd, right? That's because our experience of time is linear. But what if that's an illusion? What if causality, the rule that cause precedes effect, isn't absolute? What if it's possible, at least theoretically, for effect to precede cause? This is where tachyons re-enter the story. Tachyons, by definition, are particles that always move faster than light. But in the framework of special relativity, something strange happens when you imagine such a particle. From certain perspectives, a tachyon doesn't just move faster than light, it moves backward in time. Let's break that down. In Einstein's theory, simultaneity is relative. That means two events that appear simultaneous to one observer might occur in a different order for another. When a particle moves faster than light, the math allows its signal to be received before it's sent, at least from some points of view. This gives rise to reverse causality. The effect can occur before the cause. In the case of tachyons, a message sent from point A to point B via a tachyon could arrive at point B before it was even sent. If that sounds like a paradox, it is. Imagine sending yourself a warning about a future mistake. You receive the message and avoid the mistake, but then you never need to send the warning. So where did the message come from? This is known as the grandfather paradox, a classic problem in time travel theories. For this reason, many physicists are deeply skeptical about the real-world existence of tachyons. If they could be used to send information into the past, it would fundamentally break the logic of reality. But some scientists argue that these paradoxes don't necessarily disprove tachyons. Instead, they suggest limits on what tachyons could do. Perhaps tachyons exist, but can never be used to transmit usable information. Or perhaps, even if they could, the universe has a built-in censorship mechanism, like the Novikov self-consistency principle, which states that any event caused by a time traveler or a tachyon signal must be consistent with the timeline that produced it. In other words, you can't change the past. You can only fulfill it. Some researchers have even proposed experimental setups to detect tachyons, such as Cherenkov radiation in vacuum or cosmic ray anomalies, but no conclusive evidence has emerged. Still, the idea lingers, especially in quantum mechanics. In some interpretations of quantum theory, such as the transactional interpretation, particles are thought to exchange waves forward and backward in time. This echoes tachyon behavior. In that model, a quantum event only occurs when a wave traveling forward in time meets a wave traveling backward. No causality is broken, but the interaction itself defies classical intuition. Could this be a hidden mechanism mediated by something tachyon-like? We don't know. But the mathematics of quantum field theory leaves the door open. In fact, Feynman diagrams, which physicists use to visualize particle interactions, often include particles traveling backward in time. These are interpreted as antiparticles moving forward. But again, it challenges our everyday sense of time. So let's take a step back. Why are physicists even entertaining such ideas? Because at the deepest levels of physics, time isn't what we think it is. Many equations, including those of quantum mechanics and general relativity, are time-symmetric. They don't care whether time moves forward or backward. It's only at the macroscopic scale, where entropy increases, that time seems to have a direction. This arrow of time may be emergent, not fundamental. If so, then reverse causality might not violate any fundamental law. It may simply be something we don't yet understand, a hidden symmetry of the cosmos, visible only under exotic conditions, like those involving tachyons. Some have speculated that entire regions of the universe, or other universes entirely, might operate under reverse time. In such a world, What we call future would be their past, and vice versa. If tachyons exist and can traverse both types of space-time, they might be the cosmic ambassadors, connecting timelines, bridging cause and effect in ways we cannot yet comprehend. And maybe, just maybe, our inability to detect tachyons isn't because they're fictional. Maybe it's because they're not bound by our direction of time. They could already be here, influencing events in subtle ways, before we even know to look for them. In the end, the real question isn't just, can tachyons exist? But rather, can we accept a universe where the future can reach back into the past? If that answer is yes, then we are on the verge of a new physics, one that shatters our deepest assumptions about time, fate, and causality itself.